At 1:10 in the morning, a long Russian fuel convoy was moving toward Crimea, but from a distance it looked almost harmless. The tankers had been disguised as civilian trucks carrying milk and clean water. Yet above the road, a Ukrainian reconnaissance drone had already found them, along with something even more dangerous ahead: a damaged bridge that would force the entire convoy to slow down and compress into a narrow line. For Ukraine, this was the kind of target that could affect far more than one road. Fuel keeps tanks moving, artillery supplied, and military bases operating. But the moment the drone began sending data, Russia started hunting the signal. When the drones launched, Russia responded with the R-330 ZH Zateljammer interceptor drones, electronic guns, and small arms fire. The control links began to disappear, forcing the FPVs to use computer vision to find the tankers and keep flying on their own. Could Ukraine keep tracking the target after losing contact? Could its FPV drones break through Russian jamming and several layers of defense? And what would happen if only a few reached the bridge? Stay with Military Force as we examine how one hidden convoy became the center of a much larger battle over Crimea. Ukraine's greatest advantage was not the number of drones in the air. It was the fact that the convoy had been identified before it reached the place where its movement would become predictable. A military column can hide its purpose in several ways. Vehicles can be repainted, covered, or mixed with civilian traffic. Drivers can avoid large bases and move at night. Yet a convoy still leaves patterns that are difficult to conceal. Many heavy trucks moving together will keep a steady distance. Escort vehicles may hold positions at the front, rear, or center. Communication trucks can stay close to the commander. The route itself may also reveal the mission, especially when it leads toward a known military supply area. From above, these details matter more than the color painted on the doors. The Ukrainian reconnaissance crew did not need to read every marking. They only needed to understand how the vehicles moved as one system. That pattern gave the first sign that the column was carrying something important. The damaged bridge changed the situation even more. On an open road, fuel trucks can spread out, leave the pavement, or turn onto side routes after the first explosion. A wide area gives drivers choices, and those choices make a coordinated strike harder. The bridge removed most of them. Broken sections narrowed the usable lane, so each vehicle had to reduce speed and follow the truck ahead. The distance between them became smaller, while the order of movement became easier to predict. A long target that had been spread across several miles was now being compressed into one narrow space. Terrain was doing part of the work before the first weapon was launched. That mattered because fuel transport is not just another support task. Tanks cannot shift positions without diesel. Self-propelled guns need fuel to leave a firing point before counter-battery fire arrives. Ammunition vehicles must move between storage sites and gun lines. Engineering machines clear damaged roads, while recovery vehicles pull broken armor away from exposed areas. Every one of those missions depends on a steady supply of energy. A single tanker may seem less valuable than a tank, but a full column can support many armored vehicles at once. Losing several combat vehicles hurts one unit. Losing the fuel route can slow several units across a wider front. The bridge also created the risk of a chain reaction. If one truck caught fire in the center of the crossing, the vehicles behind it could be trapped before they had time to reverse. Those in front might escape, but they would leave the rest of the formation divided. Smoke, heat, and damaged pavement could delay rescue crews and block later traffic. Even trucks that survived the first blast could become useless if they could not leave the area. The aim, therefore, was not simply to hit the largest number of vehicles. It was to strike where one disabled tanker could change the movement of the entire column. This is why early reconnaissance was more important than immediate fire. The Ukrainian team had to resist the pressure to attack as soon as the convoy appeared. By continuing to watch, the operators allowed the road, the bridge, and the formation itself to create a better target. Patience turned distance into compression and movement into vulnerability. Yet every extra minute of observation carried a cost, because each transmission from the drone could also reveal where the people controlling it were hiding. The moment Russia detected repeated transmissions from the same area, the Ukrainian drone team stopped being the hunter and became a target for artillery. A reconnaissance UAV cannot watch a convoy in silence. It must send video, location data, and movement updates back to the people controlling it. Every transmission creates an electronic trace. One signal may reveal very little, but repeated signals from the same area can build a pattern. Russian electronic intelligence units can detect the source, measure its direction, compare several emissions, and slowly reduce the size of the suspected zone. This process does not require Russian troops to see the operators with their own eyes. Once the estimated location becomes accurate enough, artillery can strike the area based on coordinates alone. The first rounds may fall wide, but later salvos can move closer if the same source keeps transmitting. That is why a control station that stays active for too long can become exposed even when it is hidden under trees, inside a ruined building, or behind a low ridge. The system involved in this kind of search would more likely belong to signals intelligence, electronic intelligence, or radio direction finding units. It should not be confused with the Yastreb AV radar. Yastreb AV is mainly designed to track incoming artillery rounds and calculate where they were fired from. Locating a drone control signal is a different mission, and it requires equipment built to detect and compare radio emissions. Once the Russian artillery began firing, the Ukrainian crew had to react within seconds. The live video feed was cut, transmitters were shut down or moved to lower power. Soldiers spread out so that one shell could not hit the entire team. Batteries, screens, and other warm equipment were covered because Russian reconnaissance drones could use thermal cameras to search the area. The crew also prepared to leave if the shelling started to move closer. Going silent, however, created another problem. The drone was still above the convoy, but the operators could no longer guide it in the usual way. To keep the mission alive, they switched the aircraft into an autonomous or semi-autonomous mode. The onboard system continued following the general shape of the convoy and its direction of travel. It did not need a constant stream of commands from the ground. This did not make the UAV invisible. Its electronics could still produce some emissions, and any later transmission could still be detected. The change simply reduced how often the drone had to communicate and how long each signal remained active. That gave Russian direction-finding teams fewer chances to improve their estimate of the control position. The larger lesson is about electromagnetic discipline. On this battlefield, soldiers can remain physically hidden and still reveal themselves through radios, data links, and control equipment. A team that speaks for too long may be easier to find than a vehicle moving across open ground. Survival now depends on knowing when to transmit, how much information to send, and when to disappear. AI did not replace the Ukrainian operators at this moment. It bought them time. That difference was small in theory but decisive under incoming fire. The software kept the aircraft on task while the people below hid, moved, and protected the rest of the mission. Yet the drone could not keep the target data to itself, because the FPV strike team still needed the convoy's position and the short window before it cleared the bridge. To keep the operation moving without creating a long and easy signal to track, Ukraine compressed the key target information into a small data package and sent it in one very short radio burst. That package did not need to carry full video. It only had to give the FPV team the facts needed to act. The latest position of the convoy came first. Then came its direction of travel, estimated speed, and the exact point where the road narrowed near the bridge. The message could also include the safest approach route, the shape of the terrain, and the time left before the tankers cleared the crossing. Each detail helped the strike crew build a picture without opening a long conversation over the radio. This mattered because long transmissions create what electronic warfare crews call dwell time. That is the period when a signal stays active long enough for the enemy to detect it, study it, and measure its direction. A short burst reduces that window. It does not make the source impossible to find. A sensitive Russian receiver could still notice the signal, record its frequency, or mark the general area. But a message that appears and disappears almost at once gives direction-finding teams less time to compare bearings and calculate a precise location. The goal was not secrecy in the absolute sense. It was speed. Ukraine needed to pass enough information to continue the attack, then close the link before Russia could turn the transmission into a firing solution. The exact claims in the source, including a half-second burst or one specific frequency, remain unconfirmed. The stronger point is the method itself. Send less. Stay active for less time. Move the mission from one team to another before the enemy can react. Once the packet reached the FPV crew, the attack became a problem of timing and geometry. The operators used the convoy's last known position to estimate where it would be when the drones arrived. They compared flight distance with battery life, wind, and terrain. A low approach along tree lines, road banks, and damaged structures could reduce the chance of early detection. The team also had to choose which tankers mattered most. A vehicle near the center of the bridge could block movement behind it, while one near the far end could trap trucks that had already entered the narrow section. The countdown now shaped every decision. If the FPVs arrived too early, the convoy might still be spread across the road, and the drivers would have more room to escape. If they arrived too late, the tankers could clear the bridge, regain speed, and separate into smaller groups. The strike window was therefore not measured only by distance. It depended on how long the road would continue holding the vehicles together. This transfer also showed why modern drone operations are built as networks rather than single teams. The reconnaissance crew found and followed the target. Another group prepared the strike aircraft. Data moved between them, so the mission could continue even while one position was under fire or forced to relocate. Splitting those roles made the system harder to stop with one artillery attack. Now the aircraft had to survive the journey through them. The target information had reached the launch team, and the route had been chosen. Yet the bridge was still protected by the R330Z Zytel jammer and several other layers designed to stop the FPVs before they came close. The hardest part for the FPV formation was not finding the bridge. It was staying in the air after Russia began attacking both the control link and the aircraft themselves. The first barrier was the R330Z Zytel electronic warfare system. Zytel is built to detect, track, and jam satellite, mobile, and navigation signals. As the Ukrainian drones moved closer, the video feed began to break apart. Images froze, delay increased, and control commands arrived late. GPS data could also weaken or disappear, which made low-level flight dangerous near trees, road banks, and broken structures. Zytel should not be treated like a magic switch that makes every drone fall. Its effect depends on distance, power, antenna direction, terrain, and the frequency used by the target. A drone flying behind trees or below an embankment may receive less jamming energy than one flying across open ground. Operators can also try to change frequencies, reduce altitude, or use short control bursts. These methods do not remove the threat, but they can help a few aircraft stay connected long enough to reach the final approach. When the link became too weak, computer vision took over part of the mission. The software compared the camera image with the target selected earlier by the human operator. It searched for the shape of the bridge, the line of tankers, and the large vehicles moving through the narrow lane. Once the system recognized the chosen object, it tried to keep that object inside the frame and correct the flight path. This was not full autonomy. The drone was not freely searching for any target it wanted. The operator had already chosen the tanker and attack direction. The software only helped maintain the lock during the final seconds after communication was lost. That difference matters because terminal guidance is far more limited than a system that finds and attacks targets without human input. Getting through the jamming zone still did not place the FPVs over the convoy. Russian interceptor drones were waiting above the route. These aircraft carried little or no explosive load, so they were lighter and more agile than the strike drones. By diving from above, they could turn height into speed and destroy an FPV through direct impact or by damaging a propeller. The Ukrainian formation tried to make that attack harder. Some drones stayed close to the ground, while others climbed and drew attention. The group then split, forcing the interceptors to choose between several directions. A small decoy element could pull Russian aircraft away from the bridge, while the lower group continued along the roadside under visual cover. Closer to the target, Russian troops added another layer. Directional electronic guns could disrupt a drone when the soldier saw it, aimed the antenna correctly, and held the beam on it. Rifles, machine guns, and shotguns formed the final defense. Yet shooting a fast object flying only a few feet above the road was difficult, and every missed round risked striking the fuel trucks below. These defenses likely destroyed or disabled much of the Ukrainian formation. That does not mean they failed. Their purpose was to reduce the number of attackers, protect the crossing, and force Ukraine to spend more drones for every successful hit. But drone warfare is often decided by what survives, not by what is lost. After jamming, interception, and gunfire, only a small number of FPVs remained, while the convoy was still trapped on the narrowest part of the bridge. The surviving FPVs did not need to destroy the whole convoy. Their real task was to hit the points that could block the bridge and keep other fuel trucks inside the fire zone. The first target was a tanker near the narrowest part of the crossing. Once the warhead punched through the tank, the vehicle could no longer move. Its damaged frame became a barrier, and the trucks behind it lost their path forward. On a normal road, drivers might turn around or leave the pavement. On a bridge, there is almost nowhere to go. One disabled tanker can therefore stop many vehicles that were never hit. The second strike mattered because several trucks were packed close together. Burning fuel could spread across the road surface, while heat damaged tires, pipes, and valves on nearby tankers. A truck did not need to take a direct hit to become part of the disaster. If its wheels failed, its fuel lines broke, or its engine stopped, it became another obstacle. The fire then created new points of danger along the column. The third target was near the exit of the bridge. That position could trap vehicles that had almost escaped and divide the convoy into separate groups. Trucks ahead might continue moving, but those in the middle would be cut off from support. Recovery teams would also struggle to reach the damaged section because the approach road was blocked by burning vehicles and thick smoke. What began as 3 impacts could quickly become a problem for the whole route. The effect did not depend on destroying every tanker. Closing the crossing for several hours could already force Russia to change its transport plan. A longer shutdown would have greater costs. Convoys might need to take slower routes, travel in smaller groups, or wait for engineering teams to clear damaged vehicles. More escorts would be required, along with extra drones, jammers, and air defense assets to protect future movements. Each new layer would consume manpower and equipment that could have been used elsewhere. Fuel delays also spread through military operations. Tanks and armored vehicles can fight only while they remain mobile. Self-propelled guns need to leave firing positions before enemy counter-battery fire arrives. Ammunition trucks must move between storage points and artillery units. Recovery vehicles need fuel to pull damaged armor away from exposed ground. When supply arrives late, commanders may reduce movement, delay attacks, or keep larger reserves for emergencies. A shortage does not make a mechanized force collapse at once. The damage is slower and less visible. Units begin to drive fewer miles. Response times grow longer. Vehicles stay parked because commanders are uncertain about the next delivery. In that situation, Russia may still hold the same number of tanks, but fewer of them can be moved at the right time. That weakens flexibility across a wider section of the front. The pressure on Crimea would be even more serious if road attacks were combined with strikes on rail lines, fuel depots, repair sites, and maritime transport. Ukraine would not need to isolate the peninsula with one dramatic blow. A more realistic aim would be to make every delivery slower, more expensive, and harder to protect. Russia would then have to spread air defense and electronic warfare systems across more locations, reducing the protection available at each one. This is the logic of asymmetric warfare. A cheap FPV cannot replace missiles, artillery, or aircraft in every mission. But when it hits a fuel truck, a bridge, a repair machine, or a recovery vehicle, the indirect cost can be far greater than the drone itself. The result comes from the whole chain: reconnaissance, data, timing, terrain, automation, and target selection. In this case, a few surviving aircraft could create an effect much larger than the number of weapons used. That is how a tactical strike becomes an operational logistics crisis. If this operation is later confirmed in full, its importance will go far beyond a few FPV drones reaching a line of fuel trucks. It would show how modern warfare is increasingly shaped by the connection between surveillance, electronic signals, software, and timing. A convoy may look protected on paper. It can move under civilian cover, travel with escorts, and operate inside a zone defended by jammers and interceptor drones. Yet all of that protection can weaken once the route becomes predictable and the terrain removes every safe choice. AI does not make a small aircraft impossible to stop. Electronic warfare can still break the control link. Interceptor UAVs can destroy attackers before they reach the target. Soldiers with rifles, shotguns, and directional jammers can still defend the final few hundred yards. Most of the attacking formation may never arrive, but image-based terminal guidance changes the final stage, because a drone that has already locked onto a selected object may continue after the pilot loses direct control. The deeper lesson is about the system behind the front line. A tank may have thick armor and a powerful gun, but it cannot move without diesel. Artillery cannot keep changing positions without transport. Damaged vehicles cannot be recovered without engineering crews, spare parts, and working roads. Military power depends on these less visible links, and that makes supply routes part of the battlefield. Ukraine does not need every strike to destroy an entire convoy. It only needs enough successful attacks to force Russia to slow deliveries, add more escorts, spread defensive systems, and use longer routes. Over time, those extra costs can reduce the speed and freedom of mechanized operations across southern Ukraine and Crimea. In a war of attrition, the most important explosion may not be the largest one. It may be the blast that closes the right road at the right moment and keeps affecting operations after the fire is gone. Subscribe to Military Force for clear analysis of the weapons, decisions, and supply systems shaping modern war. Our goal is to explain how these battles affect both the front line and the wider balance of power. Understanding war is one step toward understanding how peace may eventually be built.